Let's begin, as we always, of course, do, with the print spooler. So printers have a lot of different capabilities, and they can have different ways of communicating with them. Lots of different ways of communicating with them. Some of them are listed here. These are just some of the ways in which you can talk to your printer, and printing is slow. But computers are pretty fast, and communications is fast. And so the host computer really needs to know how to talk to a particular printer, and it needs to know who's responsible for spooling up or storing the print job until the printer is ready to print it. And the printer may have some storage, but the computer probably has more. How does all that get balanced out? And also, how do we alert the user that the printer has run out of paper or toner or ink or something? Well, we need a way to talk to it. And that's handled by a piece of software called the print spooler. The print spooler just manages printers for you. And it's an application running on your machine like any other. It's part of the operating system. On Linux and Mac OS, the print spooler is the common Unix printing system, or CUPS. So if you ever encounter CUPS, that's just there to help you print stuff. CUPS provides a C API, and there's other APIs like a Python API. An example using the Python API for CUPS is shown over here on the right, where I'm talking to some of the machines, some of the printers that are on my home network, and some of the ones that are around the lab where I work. Printers need a printer driver. This is specialized software that handles the communication with the printer. And you might have to convert a file, let's say from some format, like a PDF, to another format, like a dot matrix image for the printer or something else. Or you might have to just wrap it in some new container. Who knows? And the printer driver also implements whatever the communication protocols are that are needed to talk to the printer and understand what the printer has and what its features are. And you add printer drivers with a remote procedure call interface. RPC is remote procedure call. It's a way of invoking a function, potentially on another machine, over the network. And the one you use is RPC add printer driver EX. And there we go. It installs a printer driver on the print server, right? You may have a computer on your network that is the print server. It's sort of responsible for managing that. And this method performs a similar function, and so on, and so on, and so on. And there's this opnum at the bottom, and that is the operation number for the RPC call. This is basically like the opcode for it. Let's think about RPC add printer driver EX. Adding a new printer is something a normal user will likely want to do, and so adding a printer is something a normal unprivileged user can do. It makes sense, right? You shouldn't have to elevate just to add a printer, right? You plug a printer into your print server, or you need to talk to you add a new computer to your network that needs to talk to a printer. You don't want to have an admin come down there and elevate and all that sort of stuff. You just want the user to be able to add that printer. Printer drivers are distributed as dynamically linked libraries for Windows, and so it contains code that executes, that runs. And it contains code that executes to set up a printer. Some printers need to have special firmware downloaded whenever they boot. It needs to check its status and so on. And that is, the DLL contains code that's going to be run whether or not anyone actually ever tries to print to that printer. So you can install a DLL, and you're going to run code out of that DLL to set up the printer. It's an RPC call, so it's potentially a remote procedure to add the driver on a possibly remote print server. So naturally, the first thing you'll think of is, I want to remotely add a malicious DLL to a print server, which can in fact be any Windows computer. And then I want to wait for the exciting various things to happen. Well, you need to log in on the remote system to do this. But it turns out it can be any login. Anonymous network share? You're good. And the code that runs, the malicious code that you've installed that will now run on the remote server, doesn't run as administrator. It runs as system. Well, surely that's better, right? It turns out it's not. System can access other domain servers in the context of the computer's domain account, but the administrator has to authenticate each time. So it's not just, it's even worse than being the administrator. And this leads to a vulnerability called Print Nightmare. And it really kind of is. This was reported at the end of 2021, just last year. And they published an exploit for it and then quickly took it down because, you should maybe not do that right away. But not before it was cloned. And if you want to see it, head right to that URL and take a look. And there are a few different CVEs associated with this, and that's not unusual. Once you find something that gives you a wedge into the system, oftentimes you find a number of things that are close to it logically, that are similar enough that you can slip in and cause problems. Like if it turns out you can install a malicious printer driver, what about a malicious scanner driver? Pretty soon you're sort of racking up the CVEs because you've gotten to thinking maliciously. What's the mitigation for this? Save trees. Don't print. There you go. Problem solved. Quit printing. Just quit it. Stop it. Stop it. Let the trees grow. The solution is patch and then patch again and then do some more patching and just keep patching. And while you're doing that, some printers may stop working, and there you go. Okay, so there's lots of stuff. How do you use the exploit? Well, we can watch this video. We're not going to do that right now, but watch it. It'll be in the slides. Watch it at your leisure. So what happened? How did this go wrong? Well, a trust decision was made without considering the trust assumptions of the print spooler. Right? There were trust assumptions made about what would happen with the print spooler, and then those were violated by the implementation of the system. And this all brings us back to the important lesson: verify your trust boundary. Verify your trust boundary. This can be hard for large systems. You got a very complex big system like Windows, and different people are looking at different pieces of it, right? So it's that old adage of everybody, all the blind men feeling the elephant and trying to figure out what it is. Everybody's looking at a different little narrow piece of the operating system, but they need to be aware of the trust decisions that are present in different parts. And you can document those in various ways to help people hopefully not make this kind of mistake. The trust boundary assumptions need to be documented, but even more than that, explicitly communicated. There's homework. The homework was to go get familiar with Keras. Hopefully you did that. Nothing to turn in, so don't panic about that. Let's go and talk about attack trees. We talked about this before. You've seen this slide. Attack is the use of exploits to achieve a negative technical impact. Attack patterns are descriptions of the common patterns that attackers use to achieve their goals. The MITRE Common Attack Pattern Enumeration and Classification, CAPEC, is something we looked at briefly before, and that's a library of attack patterns. We talked about weaknesses, vulnerabilities, and exploits. Threat modeling goes and tries to find weaknesses in your system. It pokes and prods at the design, hopefully before you've codified it fully into code, right? Threat modeling should happen early, should happen often, and should even happen, once you've built the thing. You've probably made decisions that may have changed parts of the architecture, and you should go back and recontextualize your security in terms of what you actually built. So a weakness anywhere should be included in the threat model. Include all the weaknesses. You may not address them all. You should definitely include them. Okay? And security is contextual, so you have to think about the context in which your system will be deployed. Context matters. So that might or might not be a password. Security always depends on context. The actual security of your system can depend on the path that an intruder takes through the system. Someone trying to get into this computer remotely, they may be in big trouble. They may never be able to get into it. Someone who's standing in the room can probably get in, right? And so the path that you take to get to it can matter. Someone standing outside the building where the blinds are closed, or if the blinds are open, maybe they can look through the window, see that reflected in another surface, go use the CSI enhance, and now they can get in. So there you go. Maybe we can secure this by other means. Maybe we disconnect it from the network. Maybe it's the password is on there, but the machine is disconnected, so you can't get to it over the network. That path is broken, but you can get to it by walking into the room. This is path-based security. And this is where the security of a system depends on the path that an intruder takes. A computer locked behind the door is secure against remote hacking, maybe, and there's no path on the network that reaches the computer, and so that's great. It may or may not be secure against an attacker with physical access to the building where the computer is located. Right? Maybe you can pick the lock and get in and access the machine. So you should think about the steps involved in getting access. And so what you do is you start with your goal. What's my goal? My goal is to steal data, or to access this computer I shouldn't access, or to change my grade in iLearn. Those are my goals. And sometimes there are legitimate ways to do it, right? Maybe I can just do better on my homework. Maybe I can get a job at the company that has the computer. And there are maybe less legitimate ways to do it. And so we start up at the top here with trying to access the computer. And maybe there's remote access. Maybe there's physical access. Physical access may require that I open a door. That door might be locked. Or maybe I can get the key. Maybe I can walk in right behind somebody. Right? That's called piggybacking. What piggybacking is, that's where someone badges and opens the door, and you're like, oh, thanks, and you walk in with them. Maybe you can pick the lock. Maybe you can say, I'll give you lots of money if you open the door for me. So all those are real possibilities, different ways to subvert security. And this is one way to create the graph, right? You think about the problem to be solved. You break it down into sub-problems. You break those down into sub-problems until you reach a level where you have potential solutions. And then you can evaluate those and see which ones are maybe cheaper or quicker or easier for you than others. Each one of these leads to a new goal. So all these intermediate nodes are goals. And then here at the bottom we have actual actions we can perform. So there you go. That's one way to think about breaking down an attack. You may eliminate the impossible. Right? We decide that, hey, that computer is not connected to the network, or if it is, I don't know, and I don't want to think about it, so you eliminate those. And you say, well, I can't get the key, and the person isn't going to let me blackmail them. I don't have much money to blackmail them with. They're not going to let me just walk in with them. Some places have anti-piggybacking rules. So maybe my best bet is to pick the lock. That's the solution. I'll pick the lock, open the door, access the machine, and that gives me access. And the remaining paths here, once you've eliminated once you've eliminated the impossible, whatever remains, however implausible, is the path you have to follow for the attack. You can think about this in terms of probability of success. I have 0 chance of accessing it remotely, so that's out. But maybe I have, a 10% chance of getting the key, or a 10% chance that I can blackmail the person. That might be worth it, worth a try. Okay. If we include a failure state at each level, and we assume that we're going to try, we can try multiple times, we can keep trying this until we get through, then we have actually begun to define a stochastic process. Right? An attacker might try something once and it doesn't work, but then they might try it again and again and again and again until it does. Right? So a 10% possibility of getting the key, if you repeatedly try, could become like a nearly 100% chance of getting the key. It may take you some time, but if you keep persisting at it, you may eventually get it. So we might associate probabilities with it. And we can compute the probability of success by computing the joint probability of all the methods. And so we would take the probability that, to figure out this probability, we could say, well, assume this fails. This fails 90% of the time. This fails 100% of the time. This fails 50, and that fails 90. And let's assume they all fail. All these methods fail. Then that is 0.9 times 0.1 times 0.5 times 0.9. And then I take that and I subtract it from 1, and that's the probability that at least one of these succeeds, and that turns out to be this. And then I can play the same game here, but here it's easy. And so I wind up with this probability, which is surprisingly high. It's higher than 50% because there's a small amount that means those might work. And so there you go. Attack trees come to us through Bruce Schneier, who you see over here on the right. And he's promoted their use, but he didn't really invent them. He popularized their use in security and is commonly credited with popularizing their use, and that's great, but they've actually been around for a long time. This is an example from a paper by Bruce Schneier from 1999, where he gives an example of trying to open a safe. Right? Can I pick the lock on the safe? Can I learn the combination? How would I learn the combination? Maybe I could find it written down. Maybe someone wrote the combination down and stuck it to the safe with a post-it note. Because why not? Maybe I can get the combination from a target, right? So I know someone who knows the combination and I threaten them. Or I blackmail them. Or I bribe them. Or maybe I just eavesdrop. And in a conversation that I'm listening to, they mention it. Or maybe I trick them somehow into using the combination or giving me the combination. So this is, again, this divide and conquer approach to get you thinking like an attacker. I want to open the safe. How do I do that? Maybe I can install it. Maybe I'm the safe installer. Maybe I can cut it open with a torch. Right? You try to think like this and work your way down, and then see if there's a plausible attack for you. The attack tree can be annotated in a few different ways to change and maybe improve its usefulness. How much does it cost to cut the safe open? I think that's a lowball number. Let's say 10K. How much does it cost to pick the lock? Well, okay, 30K. Maybe you got to take a lock picking class. Maybe I got to hire a private investigator to root around in their office and find the combo. Maybe I buy some remote gear to listen to their conversation. If I have 100K lying around, maybe that's enough to blackmail them. Maybe 20K is all I need to bribe them. If 20K is all I need to bribe them, why do I even bother picking the lock if that's more expensive? Why do I bother doing this other stuff, right? Take the cheapest one. And we could say, you know what, we're going to defend against all attacks that cost under 20K or 20K or less, and so we'll make defenses against this and this and this, but maybe the rest of these we think are impractical. We could annotate the graph with whether special tools are needed, right? I need lock picks for this. I might need drills. I might have to hire some thugs to threaten you. Or special skills are needed. So once we have attack trees, we can begin to think about attack graphs, and I actually mentioned that a little earlier. The idea here is, for an attack graph, I have these probabilities. Remember, we worked these probabilities out. What I would really like to capture is the notion that just because I tried this and it didn't work doesn't mean I'm done. I can, in fact, try it again. And I can, in fact, try it again. And so if our probability that we succeed is this, and I'm allowed to try, let's say, 3 times, the probability of success is not this. It's this each time, right? It's this probability each time. But the new experiment of trying this 3 times yields a probability of success of over 93%. That's pretty good, right? This is better than a coin toss. And so let's say this is probability of getting heads on your unfair coin. Getting 3 heads in a row, when you're getting at least 1 head in 3 tosses becomes very likely. So additionally, once I've bought the lockpick set, or I've done the other things, I have invested in this, and I don't have to make that investment the next time. It can be cheaper the next time through. And that's a good general principle. The cost of an attack is always decreasing. You should assume the cost of an attack is always decreasing. So if you work out what you think it'll cost to attack, you can assume that will be less in the future, and then less after that, and so on. Right? Not just because people buy things, but because things get cheaper. Right? Information gets more accessible. People publish new YouTube videos that find better ways to do it. Cost of attacks is always going down. So here's a little aside. The Flipper Zero is this little device. It's $169 if you buy one today. And you can add on some stuff to it. What is this little thing? This little guy speaks, has a little radio inside it, a software-defined radio that runs on a few different frequencies, and it's very common consumer-grade frequencies, and it can listen on those frequencies and decode certain signals, and it can broadcast on those, and you can control it with software that you can write and upload to it, and you can plug in other boards to it. You can't see it from here, but on this side there's a pinout that you can plug other boards into, and like the Wi-Fi development board here and the prototyping board. And so you can get this to do neat stuff, and people have used it to do things like remotely access the Teslas. So there you go. You can in fact unlock my car with this little guy, right? I have a rolling code on my keys, but if I go far enough away from my car, then I can record the unlock button with the Flipper Zero, and the car doesn't hear it. And then I go to the car and play it back, the car unlocks. Pretty neat. That's the principle behind something called Roll Jam. If you want to go Google Roll Jam, ROLLJAM, you can find a device that will steal that information specifically made for cars. Fun stuff. So we've taken our attack tree, and now we're turning it into an attack graph. And you'll see what's gone on here, right? Every time we try something, we come back down here to the retry, which takes us back up to the top. And so now we have a stochastic process. We have a process where we're repeatedly doing some probabilistic operation, and that can, tell us some new information. Like, given these probabilities, the expected number of trials until we see the first success, accessing the computer, is just under 2. So we might try it once, we might try it a second time, and then we've probably gotten in. So that's not good. The structure begins to get more complex as we add this information, but that's what computers are for. Every piece of information that you add to a security model increases the apparent utility of the model. And notice the word apparent, okay? It increases the apparent utility of the model, but it also increases the possibility of self-deception, right? So I come in here and I think, well, that's got 0 probability of success. But then it turns out my people are doing this all the damn time. I've told them not to, but they all do it. So maybe that's not 0. So I've deceived myself about the probability, because since that's not 0, this number is much higher than I thought it was. And the whole thing is much more likely. So the more information I put in to the model, the greater the possibility that I am deceiving myself about security. So you need to think about these things very carefully. So document how you know, and also how well you know, each piece of information in the model. And it doesn't have to be a lot of stuff. You can just say, I'm making this assumption based on this rule. And then if I observe something later, I can change it. I'm making this based on the current price of this particular tool on eBay or on Amazon. And if that, I'll check it again maybe in 6 months. And the other thing to think about, and believe it or not, this is a real possibility, is did you get your information from a potential attacker? So I might get my information by going and talking to people, someone who's in IT who's telling me stuff, and maybe they are part of the threat, or maybe I'm getting it from from an external source that turns out to actually be an attacker. That can and has happened. So back to the attack graph. This organizes the different steps, and you can see I've highlighted the ones with dashed lines where the probability is non-zero. And this lets us think about the system from the point of view of the attacker. And then we can introduce some elements to try to break up the path through the graph wherever there's a concrete action. For example, here they're getting the key. Well, maybe if we do a better job of securing the key, we can reduce this probability. And so we require that the key be on a keyboard, that you have to check it out each time you want to use it. It has to be returned. Now I know who has the key, and that incentivizes you to return it, because if someone uses the key to get in, I can go point the finger at you because you were the last person to check the key out. And so maybe that probability goes down. Okay? Now, suppose that you have a very detailed attack graph. Maybe you do this by observing many successful attacks on various systems. Now, suppose you have a ton of alerts arriving at your Security Operations Center, your SOC. You're being flooded with alerts. You'd like to know, are some of these things just routine surveillance, just internet chatter, just, false alarms? Or are some of these things part of an attack? How could I tell? So let's think about these two things. I may have these attack graphs that I've built by observation. I have all these alerts. Can I combine them to help me sift through the alerts? If the actions in the attack graph can be correlated to the alerts that you're receiving, you can probabilistically recognize that some of the alerts are part of an attack. Okay? And then you can ignore everything until the threshold gets reached. That is, ignore things until an attack becomes evident, right? Reaches some threshold likelihood from the data. This is great because this dramatically reduces the volume of stuff that you have to consider. Right? And so instead of getting floods of alerts and ignoring most of them because you don't have time to sift through them, you're instead being told, we think with this fairly high probability, this kind of attack is happening. And then you can take an action. The downside is this delays detection, and it may give time for an attacker to operate undetected, and it may also be used by an attacker. They may launch 1,000 different attacks, all of which will flood you with information while they're actually doing the real attack, right? They flood you with attacks that say someone's trying to get into the computer, they're trying to get in the computer through the network, and you're running around trying to do that. Meanwhile, they've stolen the key and go in the room and log in. Okay? Real possibilities. But it does help you reduce the scale and the scope of the stuff that you have to respond to. And if you've ever worked in a security operations center, that's a big deal because you are flooded with alerts. You can think of information gain. Okay? As an attacker works his way through these paths, they gain information about your system and about the capabilities of your system, and maybe even about your defenses. So let's take the picking the lock path. That was the highest probability one. Let's pick on it. The attacker tries it, and they fail. But they know something. They've learned something. They have learned the type of lock. Maybe they've learned the number of pins, and they had to stop because they ran out of time. Maybe they've learned that they really need a different type of torsion wrench, which is a little thing you put in to put pressure on the lock while you're picking it. Maybe they need to bring a different set of picks with them next time. And so, since they know what the lock is, what the type of lock is, they could maybe go out and buy one. And they can practice on it till they're really good at that type of lock. Buy a couple different ones, right? Getting really good at one lock does not make you better at all locks of that type. Buying a couple of them can make you better at all locks of that type. And so they get really good at it. And so when they come back, they have gained information. They even have gained new skills. And that probability is not 50% anymore. It could be nearly 100. Okay. The probabilities change because of information gain. The principle here for you, as someone trying to build secure systems, write secure code, defend a system, is give as little information to an adversary as you can. If you've got a thing securing a door, maybe put a sticker over, at least put a sticker over the model number of it. That's not a joke, right? I mean, if the adversary knows what the system is, they can take advantage of that. That's called operational security. That's OPSEC. Deny the adversary information whenever you can. Even trivial information can be weaponized. Information gain is one of the best things that can happen to an attacker. Gaining information about your system really improves their ability to assess whether and how they can get in. Design systems to provide the least information possible to an attacker. And this has to be balanced with utility. People have to be able to use the system, but you define your policies and procedures so that people can just use the system without having to know a lot about it. Maybe that's good, but it can also interfere with your ability to diagnose problems, etc. But you get the idea here. Deny the adversary information. Remember utility and confidentiality. Remember the Parkerian hexad, which you see over on the right. It has utility here and confidentiality up here. And you can sort of think of those as maybe being in a bit of tension, right? I need information to do my work, but you want to deny information whenever possible. Okay. So we think of the information we have to protect as confidential information. But an attacker may not necessarily need that confidential information. They may be able to do what they want to do with information about that information. Metadata, right? Other information that may reveal something. Okay? And that can come in many different forms. We saw a while back people, you use a side channel to perhaps break encryption. Well, you could maybe use timing information to determine something about what's going on. Okay? I swipe my fake card and I look at the response, how long it takes to respond. Maybe I'm sniffing the signal with a little tool that can record the transaction. I then go away and I look at what I learned. And I find out, okay, it looks like it must be this model of reader because it took this long to respond and because it had these properties to the response. Okay, I'll go out and buy a few of them and I'll see if there's vulnerabilities in them. Okay? So because of this, you should give a little bit of thought to what information you're exposing inside channels in your design. This is hard, obviously. You want to think about the main purpose of your system, but you should give a little bit of thought to other trails and other information that you may leak out. Leak as little information as you can. Attack graphs can be built in many different ways. The one way to do it is say a node is a security state. So door locked, door unlocked. That's a good security state. File encrypted or unencrypted. And you can have the edges represent actions. We didn't do it this way in the slides, but you can easily imagine that I start out with the system in a particular security state, and then I have different things that can change the state, right? I unlock it or unencrypt or do something else. This has an advantage that it's very concrete, but it can be very hard to develop because I've got to think about all the security states of the system, and that's hard. Alternatively, I think like an attacker, and I use the divide and conquer approach we saw from the attack trees earlier, the Buchneyer, the attack trees. I take a goal for the attacker, and I begin to break that down into sub-goals, and I work the problem until I arrive at possible solutions. Along the way, that tells me what the security states of my system are. See? Right? I'm trying to get into the room, but the door is locked. Oh, door locked is one. And so I can use the attack tree approach, the divide and conquer approach, to then help me identify the intermediate states to then build a more rigorous attack graph. Attack graphs are often more useful in terms of my ability to analyze them. Right? For a simple system, an attack tree may be great. That's certainly not doing nothing. That's not doing something useful. for a very complex or a very big system, or a system where I'm really super concerned about security, maybe I want something like an attack graph that will let me do deeper analysis. So here's an example of an attack graph. No access at the top, but I'm able to get into the facility. The door is locked. Maybe I can pick the lock. Now it's unlocked. I can open the door. Now it's open. And then I enter the room and I have access. Okay, that's the dashed path through it. So this is me revisiting that initial graph that we did and then turning it into an attack graph. And along the way, what I haven't included is every time I fail, what do? I go back up to the top. I just reset and try again. And so there's more detail, and this can expose new things. For example, it can expose choke points. We would call these articulation points maybe in the graph, places where we can interrupt the attack. And right here, everything has to go through door open. Great. If we can detect the door opening and immediately turn everybody's attention to it whenever the door opens, right? Whenever the door opens, or when it's let's say, when someone turns the knob or they turn the handle, the camera turns on, we take their picture, the information gets transmitted to our security guard who looks at it. Maybe that is enough to interrupt this and prevent this whole family of attacks from being successful. Okay, because all the paths go through there. And we discovered that because we built this attack graph, right? This is not super clear from the attack tree, but it may be clear from the attack graph. The attack graph is often more useful than the original attack tree. It's harder to construct and can be more complex. Attack graphs can be formalized and made rigorous. That's, of course, within the scope of known attacks, right? It's harder to build an attack graph for an attack you don't know about, right? So I'm not aware of Rowhammer. I don't know it exists. I'm not building it into my attack graph. This can allow the attack graph to be used for a number of purposes. You can compare different solutions, right? If you do this early and you realize, hey, some things don't go if everything went through this one node, maybe there'd be a way for me to check it in that way or prevent it. Maybe better. Estimating the cost of security, right? So if I look at different graphs, I may realize if I could find a way to get rid of this whole branch, I could use cheaper stuff, right? Or deploy less security. Measuring the value of the security that you currently have, right? Maybe I compare two different attack graphs. I choose the one that has a lower probability of success overall. Great. Or maybe even automating attack detection like we talked about before. If they're present and I can map my alerts onto the graph, then I can detect attacks. Well, that's all good, but if the attacker gets your attack graphs, that can be a big benefit to them because now they know way too much about how you're defending your system, right? Now they have sort of the crown jewels of the security, which is why I didn't give you the attack graphs for any of the other stuff that I've done. The downside to attack graphs is they become very complex very quickly. It's the state explosion. The better the information you have, the more detailed, more careful, more conscientious work you do, the worse things get. That's a real attack graph from paper. And it's not that complex yet, but it's going to get that way, right? You can sort of tell that's happening. Here are a couple of papers that discuss that you can have a look at, including the Schneier attack trees. That's well worth a read to let you know more about it. That's it.